Welcome to This Explainer. Today, we're doing something that is honestly incredibly fun and a bit unique. Instead of just staring at dry, polished corporate documentation, we are going straight to the source. We're going to break down a student's actual handwritten lab notebook. And through these really meticulous field notes, we're going to uncover the raw core mechanics of MongoDB. Basically, we're getting a behind-the-scenes look at exactly how NoSQL databases function right at their foundational level. Okay, let's dive into this. Have you ever wondered how the apps you use every single day manage to store, sort, and retrieve literally millions of pieces of information without just, freezing up? Well, for decades, the answer was rigid tables. Think of massive, super strict spreadsheets. But modern data is messy, right? It's varied. It doesn't always fit into a perfect little grid. And that is exactly where NoSQL databases like MongoDB come in. They offer a completely different way to handle massive data without all those strict structural constraints. Our whole focus today is to deeply understand exactly how these core concepts work under the hood. So here is our roadmap. Treating this lab manual as our developer's field diary, we're going to cover 1. Entering the NoSQL world, 2. Finding data with queries, 3. Analyzing data via aggregation, 4. Optimizing speed with indexes, and finally, 5. Mapping real-world locations. Let's get started.
All right, Section 1. Entering the NoSQL world, from rigid tables to flexible filing cabinets.
So if traditional databases are like those rigid spreadsheets where every single row absolutely must have the exact same columns, I want you to imagine MongoDB as a highly organized digital filing cabinet. You can just toss all sorts of different folders in there, and the system easily accommodates them. The fundamental unit inside that filing cabinet is called a document. It's a flexible JSON-like record. Instead of forcing your data into rigid rows and columns, it uses what we call key-value pairs. Think of name mapped to Ankit or age mapped to 22. Because it's so flexible, one document in our filing cabinet might have a phone number while the next one doesn't. And the database doesn't crash. It just naturally adapts. Diving right into the student's lab notes here, we can see the raw syntax of how data actually enters the system. Notice that insert one command being written out by hand. They're passing in a set of curly braces containing fields like name, age, USN, phone number, and address. And then, right below it, they step it up with insert many, literally dropping an entire array of these documents, multiple students at once, straight into the database. This right here is the core mechanism of populating our digital filing cabinet. And this brilliantly illustrates what happens next. Once the data is in there, things inevitably change. On the left, we're looking at the update one method. The student is telling the database, hey, find the document with the address Bangalore and set its new address to Delhi. Then, on the right, we see the database's actual console output. It fires back with acknowledged true, matched count 1, modified count 1. This is literally the database talking back to us, proving that our core modification mechanic worked perfectly. Moving on to Section 2, finding data with queries, asking the right questions. Now, having a million records means absolutely nothing if you don't know how to ask the right questions to get them back, right? In MongoDB, the core tool for this is the query selector. These are special operators that basically act as highly precise filters. They scan through thousands of documents and pull out only the exact ones that match what you're looking for. The student's notes outline these mechanics beautifully. The EQ selector is your exact match. Mechanically, it scans for an age that is exactly 21. If you need a range, well, you use $GT for greater than, which filters for anyone strictly over 21. And then there's the $in operator, which is just a fantastic shortcut. It lets you pass in an array like 19 and 22, and the database will snatch up any document that matches either of those values. But as we know, real-world data requires much more complex questions. Here in the lab notes, the student explores logical selectors. They're actually combining conditions now. Just look at that $sand operation. They are commanding the database to find students who are older than 20 and have a quiz score greater than 80. Below that, and $or operation casts a wider net, finding students younger than 20 or who have a homework score less than 50. It's incredibly powerful to see this logic written out entirely by hand. Which brings us to Section 3, analyzing data via aggregation, the data assembly line. I'll be honest, this is one of the most exciting core mechanics of NoSQL. To really understand an aggregation pipeline, you need to picture a data assembly line. It's a dynamic, multi-stage factory process. Raw documents enter on one side. Then, step by step, they get filtered, broken apart, grouped together, sorted,
And finally, they emerge on the other side as a completely transformed, aggregated set of results.
Let's see how this actually builds a sequential flow. Typically, an assembly line works in these exact steps. Step 1. Match. We filter down to only the data we actually care about. Step 2. Unwind. If we have a list inside our document, we deconstruct it so we can analyze each item individually. Step 3. Group. We literally smash the data together to calculate totals or averages. And finally, Step 4. Sort. We order the results so they actually make sense to us humans.
Now, what's really interesting about this slide is seeing this exact assembly line applied to a database of restaurants. Follow the student's handwritten code here. First, $match filters for restaurants located in core Mangala. Next, $unwind breaks apart the reviews array, creating a separate document for every single user review. Then, $group takes over, calculating the average rating and summing up total reviews for each restaurant. Finally, $sort orders them with the highest average rating at the top. You are literally watching raw data get sculpted step by step.
And the mechanics inside that grouping stage are seriously vast. Here, working off electronic sales data, the notes show how to execute specific mathematical operations. By using $average, the pipeline automatically computes the average price of smartphones and headphones. Right below that, the $min operator scans the grouped items to find the absolute lowest price. It takes a massive list of individual sales and transforms it into high-level business intelligence.
Moving on to Section 4, optimizing speed with indexes. The fast lane for data.
So if you have millions of documents, all these queries and pipelines we just learned could theoretically take forever to run. How exactly does the database manage to search thousands of documents without slowing down? Well, the answer is an index. Think of an index exactly like the glossary at the back of a massive textbook. If you want to find a specific word, you don't start reading the book from page 1, right? You jump to the glossary, find the word sorted alphabetically, and it gives you the exact page number. A database index does the exact same thing. It creates a fast lane so the system doesn't have to scan every single document. The lab notes detail 3 major types of these fast lanes. A unique index forces a strict rule, saying no 2 documents can have the same value here, which is perfect for things like user email addresses. A sparse index is incredibly efficient. It only indexes documents that actually contain a specific field, saving tons of memory. And a multi-key index is just fascinating. It actually indexes elements inside an array, meaning searching through a massive list of restaurant reviews becomes lightning fast. So the crucial point is how simple this optimization is to actually implement. Looking at the handwritten code, you see create index contact mail 1 unique true. With just that one tiny parameter at the end, the student has forced the database to never ever accept duplicate emails. Right below it, the sparse true syntax does the exact same magic for the location field. It is a massive mechanical upgrade with just a few keystrokes. Finally, Section 5, mapping real-world locations, going beyond simple text. This is where we go beyond simple text and numbers and actually map real-world locations. To do this, MongoDB uses something called a geospatial index, specifically a 2D sphere index. We aren't just storing words anymore. This core concept allows the database to understand that it is working on a round, physical, Earth-like sphere. It can actually calculate physical geometries, distances, and intersections across the globe. It's wild. Just look at this incredible entry in the lab manual. The student is inserting real-world coordinate pairs, exact longitudes and latitudes. -73.965, 40.7829. That's not random data. That is literally Central Park in New York City. Below it is Times Square. Below that, the Brooklyn Bridge. And in step 2, they run create index location 2D sphere. The moment that command runs, the database suddenly understands the actual physical distance between those real-world landmarks. And that is the true power of understanding these core concepts. We have journeyed through the students' handwritten notes, starting from just tossing simple JSON documents into a digital filing cabinet, to combining complex logical queries, building data assembly lines, optimizing speed with glossaries, and finally mapping the actual physical globe. Now that you understand the raw mechanics of how NoSQL databases really function under the hood, what are you going to build with these building blocks? Thanks for joining me on this explainer. I really hope you found it as fascinating as I did.